All right, good morning. So this is the second keynote in the series of hopefully 4 keynotes we'll have. And so we have the pleasure of introducing Michaela Blott, who is Director of Engineering at Xilinx. And she will be talking to us about FPGAs and neural nets. All right, thank you.
Thank you very much, François, for the kind introduction, and also well done for pronouncing Xilinx correctly, because it's like even in the news we were the other day, and the reporter said Xilinx. It's, oh my God. So at least all of you know now how to pronounce it correctly. It's just simply Xilinx. So the topic of what I'm going to talk to you about this morning is machine learning for embedded systems. This is very much the focus of my current research agenda. And what I'm trying to do here is I want to convey some idea of what are the challenges when enabling an AI in embedded compute systems. So for example, what does it take to bring machine learning to self-driving cars? What does it take to have a voice-activated Hoover that you can actually talk to and tell it when it missed the spot? Or, I mean, there's numerous applications, and it would take far longer than 45 minutes to iterate all of those. There's a gazillion of things that you can do when you bring artificial intelligence or machine learning capabilities to embedded compute environments. Okay, so more specifically, here's what I've prepared. So we'll start off with a little bit of background on Xilinx. I'll tell you who we are, what we're doing, and why we're doing what we're doing, and what I want to explain a little bit of what are the challenges that we're facing in the semiconductor industry. So what are we actually battling with? And then we'll swing over and we'll talk a bit about machine learning, about the algorithms used, and what the challenges are with these algorithms when you want to implement them on hardware. And all of that will actually set the context for the research, which, as I said before, is focused on enabling machine learning in embedded compute environments. So I'll tell you all about the work that we're doing inside my team, and then hopefully at the end we have time for a summary and many questions that you may have. Okay, so let's get started. So who is Xilinx? So Xilinx devices are deployed absolutely everywhere, yet many people actually don't know who Xilinx are, and that's absolutely fine. So let me tell you, Xilinx is a fabless semiconductor company which was founded in Silicon Valley over 30 years ago. Today, it's relatively modest in size, and that's because it's fabless. It's 3,500 employees and has $2.25 billion in annual revenue, so it's doing quite well. The thing Xilinx is best known for is they've invented the FPGA. May I ask, who of you actually know what FPGAs are? Why, that's pretty good. So you're doing a good job here. So I don't actually have to explain too much about FPGAs, but the first thing that's important to know, they have changed a lot since they were originally invented, right? This was the very first FPGA that was shipped back in 1985, and it had 128 lookup tables, and I assume most of you know now what lookup tables are. And over 30 years, we have now 1.7 million lookup tables, which are significantly more complex and significantly more. So that's like 4 orders of magnitude in growth. Okay, so you have a rough idea what FPGAs are already. When people ask me, like my grandmother asked me to explain what it is, I mean, the analogy that I always bring is it's the chameleon amongst the chips, right? There's processors, there's memories, there's many devices in between, and the FPGA you can actually configure to whatever it is that you want to have, right? It can be a processor, a memory, or it can be something very specific to a specific application. So that's the key advantage that you get by the FPGA, that you can actually configure it for different hardware functions. So if you look at the FPGA technology that we had over time, like this is on the left-hand side what it used to be. It was literally a 2D array of simple lookup tables that can implement digital logic, right? And functions, or functions, and so on. But then over the years, what we've introduced is different types of elements. So you didn't have just the the bit-oriented logic function that you could implement, but we also had word-oriented multiply accumulators, what we call DSP blocks inside the FPGA, were introduced, as well as memory components, and they were kind of implemented as columns that sit inside the chip. And then since the last couple of years, we actually started building, we actually pioneered die stacking devices, which is, so it used to be that you had a package for a semiconductor and you put exactly one die in, and die stacking meant that we actually can put multiple dies in. So initially they're actually side by side, and they're interconnected through an interposer with lots of connections in between, which means that you can now significantly increase the size of what you can pack inside a package. So those are kind of the big cornerstones in the development of the FPGAs. And in fact, I'm actually not supposed to call them FPGAs anymore. So they're big about this term, all programmable devices. I'm personally not quite comfortable with it yet. So I have to say it like 100 million more times. But the fact is, I mean, it's much more now than it was like 30 years ago. The key thing for the computer science students amongst you is it is not, you don't program them like you program a processor, in that you actually write a program which is loaded on the hardware and then run. With an FPGA, your program is actually translated into a hardware configuration that sits then in the table values inside the chip, and switches are basically configured for your program, right? So it goes through this long process, which is called synthesis, place, and route, before you can actually run it. But then you actually have a hardware accelerated circuit. So as I said, the key benefit of the FPGA is that it can be anything, right? It can talk any voltage levels, any frequencies, any protocols. And because of that, they're absolutely everywhere, right? From your dishwasher, which might not be the most exciting application, but they're also sitting in Mars rovers, MRI scanners. They're going to be autonomous driving cars, 3D televisions, augmented reality, and whatnot. The potential of these customized hardware architectures is as follows, right? So if you, let's say you have a basic task at hand, something like x equals a plus b multiplied by 256. So if you run that now on your processor, then it gets translated in a series of machine instructions, right? Where you first have to load your value A into a register, then you have to load your value B, then you have to load the constant, then you carry out an add and a multiply, and then you store the value back into memory. So that's actually 6 cycles of compute that you have to carry out. And typically your processor will be clocked at 2 gigahertz or 2.5 or 2.9, something in that range, right? So what happens on the FPGA is now, so your registers A and B, your variables, they actually become wires, right? They are signals, electrical signals, and they feed straight into an adder component, and then they feed straight into a shifter which shifts by 8, because that's equivalent to multiplying by 256. So that takes exactly 1 cycle to compute, and typically an FPGA nowadays would clock at around 400 megahertz, right? So you see a little bit fewer cycles, longer clock frequencies compared to the processor, which will take more cycles but run a little bit faster. So the kicker about the left-hand side is you don't have to fetch the instructions, you don't have to decode the instructions, you don't have to fetch the data or store it back. And also, you have customized arithmetic operations. So there's not an ALU which can compute, add, multiply, or whatnot. You actually have very specific hardware components instantiate that do exactly what you want it to do. So what happens is now, if you look at this level, the performance that you're going to get, I would say it's kind of on par, right? One will do 2 ops in 6 times 0.5 nanoseconds, which is 0.67 gigaops per second, whereas the FPGA does 2 ops in 2.5 nanoseconds, so that's 0.8. There's not much of a difference. Now, the exciting bit happens is when you scale it out. Because the one on the left-hand side is so much smaller, I can instantiate literally 10,000s of those inside an FPGA, right? So you can arrange them task parallel and pipeline fashion. You can go data parallel if you like. So you can have 10,000 of those, whereas on a processor, I mean, the largest Xeon processors have something like 28 cores, right? And this is where the performance comes from. So this one on the left-hand side will scale to something like tens of teraops, whereas the one on the right-hand side will be hundreds of gigahops to maybe 1 or 2 teraops, right? So this is the promise, and this is what people are getting so excited about by FPGAs. The second part, which is perhaps a little bit maybe less obvious to see straight from here, is actually the power consumption, right? Because you are not fetching instructions, decoding, reading data, writing it back. Because you save on all of that and you have customized operations, the power consumption of your implementation will also go down. So that's the promise. This is actually my team, just to switch back to who we actually are. So we're part of the overall Xilinx research organization. We're at the moment a total of 9 researchers coming from all over the world, from China, Australia, Turkey, Spain, everywhere. We also have Irish people. We also have a very active intern program. We have typically between 6 to 10 students or visiting scholars at any given time. And we've just recently got funding for an IDA, by the IDA for building out an AI lab. So we're going to add another 8 to 9 positions to the team. That's going to be big. So let's talk about the challenges in the semiconductor industry that we are actually worried about. The first one you surely have seen already, right? Clock scaling has slowed down since 2005, approximately. Right? If you look at your processors, when you buy a new laptop or something, nothing much has happened in clock speed, right? They're somewhere between 2 and 3 gigahops since an eternity. That's one. So I'm not getting more benefit by going to the next generation of my devices by scaling the clock frequency up. This is very limited. The second one is end of Moore's law. Who of you has heard about end of Moore's law? Wow, that's great. Yes, I mean, originally it was all about, you know, the number of transistors doubling in the devices every 2 years. And the term is used very generally. I mean, when you look in the news, one day they say, well, Moore is dead. The next day they say he's alive and well and kicking. And then they say it slowed down. No, all is good. The fact is it's a struggle. And if you use the term loosely as increasing the number of transistors that you can pack inside the device becomes increasingly challenging. And that's literally because they get so minuscule. I mean, you have here on the x-axis the size of a transistor. So that is a 90 nanometer. I would say that was probably about 6 or 7 years ago. That was the size of a transistor. Then it went to 65, 40, 28 nanometers was about 3 or 4 years ago. We're at the moment shipping 14 nanometer devices, and we're going to crank out 7 nanometers in the near future. So we're clearly still scaling, right? We're still reducing the size of the transistor. But it takes so much effort to getting them small, right? It needs really sophisticated equipment to actually build them with the necessary precision at the technology node. What that means is basically it gets really expensive. So the cost per transistor has actually been increasing since 28 nanometers. And that's a problem, right? Which means, I mean, when you buy a new laptop, you expect that when I buy a new laptop in 2 years, it costs the same money, but it'll be faster, right? That's kind of the expectation that we have, same with mobile phones and so on. Well, we as semiconductors, we still want to earn our margin, right? So now that our cost of building devices is going up means our profit margin is shrinking, and that makes us wonder, well, should we actually build those devices? So the whole economics around building, packing more transistors inside the devices becomes increasingly questionable. Now here's another one, Dennard scaling. Do you guys know what end of Dennard scaling is? Okay, you were doing really well so far. so Dennard scaling was saying that as we shrink the size of the transistor, the power density will stay the same, right? That was what it used to be like a few years back. And then Intel started crying and said, no, it's not working for us anymore. And they had a really doom and gloom diagram that they published, I think it was about 10 years ago, which predicted that the Pentium processor, the surface temperature of the Pentium processor, will actually become as hot as the sun's surface. I would say probably around now. and luckily this hasn't happened, right? There's numerous technologies brought in, shrinking the core temperature of the devices and so on, to actually make the chips operate at a decent temperature. But the fact is, your processor is hot enough to fry your breakfast egg if you would like to. So the overall, right, power dissipation is a huge issue for us, right? So those are really the key problems in the semiconductor industry, right? We're out of tricks, right? We can't easily pack more transistors into the devices. We can't scale the clock up, and we're battling with power consumption and the heat that the devices produce. Those are the constraints that we inherently have, which means that we can't just keep going on programming as we do and just expect the hardware to get faster and faster and more efficient, because we're basically out of tricks at the moment. Maybe there's a super genius coming up with something in the near future, but until then, there's a challenge. So let's take a look at what machine learning actually requires. So there's an awful lot of headlines about AI and machine learning in the last year. I mean, back in 2016, the New York Times had that headline, "The Great AI Awakening." And, you know, it sounds awfully doom and gloom. And every month there's something new in the newspaper, from Elon Musk, you know, having this open letter to ban killer robots, to Stephen Hawking to telling us to abandon the planet. I mean, you know, it's everywhere. So, and whether you want to get worried about this, I leave that entirely up to you. But the fact is, right, machine learning works really well for an increasing amount of use cases, right? And also, to be very clear, it's not a fashion, right? This is not something that will go away. That has come and it will stay, guaranteed. So the most predominantly used algorithm out there that we see from our side are neural networks. Are you guys familiar with neural networks already? Great, great. So, I mean, they're based on simple models of the human brain, right? You have neurons and synapses. Other than that, I don't think they're very much related, but let's say they're modeled after that. The bit why everyone in the semiconductor industry is excited about it is because they have this theoretical property of being a universal approximation function. So it can empirically outperform any other approximator functions if you make that neural network big enough and you throw enough training data at it. So this is a really powerful statement. I mean, of course, they can get ridiculously complex, and they get so big and compute intensive that you can't implement them realistically anymore. But still, this is a very powerful statement. It also means that they solve problems that haven't been solved before, and there is an increasing adoption for new use cases. Right? So neural networks, I mean, the beauty of it is you actually don't need to be a domain expert to solve a problem with this. You just throw the neural network topology at it with enough training data, and it solves it. So, for example, if you were tasked to write a program that recognizes a cat, right, you would need to know a lot about cats. You need to know it has 2 ears, it has a nose, it has 2 eyes, it can have all these different positions, right? If you have a neural network, you don't need to know that, right? You just throw enough pictures of cats at it, and it'll figure the rest out itself, right? So those are the powerful characteristics that it has, and why it is finding increasing adoption in numerous use cases. So the challenge with neural networks is exactly that, right? Because they can solve any problems, there's a really diverse range of applications. Right? You have the Google Translate, the AlphaGo for strategic gaming. You have recognizing malaria-infested cells for medical diagnosis. You have robotics that you want to control with voice or with visual stimulus. You have automated driver assist, recommender systems, hearing aids, you name it. And every single one of those will require a very different type of neural network, right? There is not just one that will solve all of those. The second part is And that's really important for us. It's for every use case, there's a different figure of merit. So, for example, for the malaria-infected blood cells, you can get a very small network with a very high accuracy. You don't care whether you have the result in a minute or 5 minutes. It doesn't matter, right? So you want to have a high accuracy and you want to have a result, within a few minutes would be amazing, okay? Then you look at a recommender system. If you don't have the suggestion for the next movie to watch within 30 seconds, the person has switched off and moved on to something else, right? So recommender systems need to have real-time behavior. Similar user experience for cloud-based systems, for example, chat windows, they have a defined limit of 7 milliseconds where they need to react. So again, they require short latency. Then you look at driver assist. I mean, recognizing the difference between a stop sign on a t-shirt and a stop sign, a real stop sign, is imperative, right? So they need to be 100% accurate, whereas a recommender system really doesn't have to be 100% accurate. A good bet at what you want to see is probably good enough. And then you look at hearing aids. I mean, hearing aids, power consumption and latency are the kicker, right? I mean, first of all, you need to have the noise filtering instantly, right? Latency is very important, but also battery, right? Power consumption. You can't be wearing a battery pack on top of your head to power the hearing aid, right? So it needs to operate on a minuscule power envelope. So very different type of characteristics depending on the use case. The third challenge is it's very compute and memory intensive. So if we look at the compute of a neural network, and I think you probably know this already, right? It's basically linear algebra, typically implemented on floating point parameters. And you would have, for example, the very popular AlexNet, VGG16. They take hundreds of megabytes of data for storing the model size. So for every image that I want to recognize, I need to access every single weight in my model. So I need to access hundreds of megabytes. You know the cache sizes that we have on your processors nowadays. So this far exceeds typical processor cache sizes, which means you're getting lots of cache misses, which slows down the whole program. So that's a problem. So memory footprint. Second part is compute. So AlexNet is 1.5 gigaops, and that's actually a small network for every single image that I want to recognize. So if you want to do real-time behavior, 30 frames or 60 frames per second, you have to do 30 times 1.5 gigaops, right? So it's a huge amount of compute that is required. And those are the kickers, which are directly on crash course with what we talked about earlier, right? End of Moore's law, so limited performance, power being an issue, and so on. So this is the key challenge when you're going to embedded compute systems. But there's more about machine learning that troubles us greatly. One is, all of these networks, they're changing, right? There's not only different networks for different use cases, but also it's highly volatile. There's every week there's new papers coming about which way we should do neural networks. So you don't need to be an expert to see the difference here, but if you look at the different type of networks, right, number of layers has changed, the type of layers, residual layers, inception layers, data representations, graph connectivity, you name it, right? So it makes it, again, very hard to bring specialized implementations for these neural networks as they're still highly volatile. And the last problem for us in the research community is it is a humongous design space to play with. So first of all, as we said, there is already a range of machine learning tasks, right? There is much more than just image classification or recognition. There is voice control, noise filtering, gaming strategy, you name it. Every single one of those, you can have different types of neural network topologies that they implement them. And for every single one of them, you can train with different training data sets, right? So for example, for image recognition, you could have Coco or Pascal VOC, right? And depending on which data set you use for training your neural network, you actually get a better or worse results. So the error rate of your network will change, which is quite a struggle. On top of that, is if you take the same network and you run it in different machine learning frameworks, you get different results too. And that shouldn't be. That is purely wrong. Right? There's numerical errors implemented within these frameworks that accumulate massively and then yield to different results. So the issue is that I can't just take one network, trained network from one framework and run it in the other one and expect the same result. The big issue. And then we can build each of these networks for different types of compute, different types of activation functions, nonlinearities, numerical representations. We can use different hyperparameters during training. For example, we can adjust the learning rates. We can use different type of regularization schemes. And finally, we can use different end devices. We can use GPUs to implement it. We can use FPGAs. And then within these devices, we can have different implementations. So every single one of these combinations in this graph will actually yield to a different point in the design space. It will provide the end application with a different compromise of error rate, right? So accuracy that the network achieves, cost of the implementation, throughput that is achieved, latency, and power, right? So it's a challenge and it's an opportunity. So there's basically, this is the graphs that we're discussing most of the time. So you have on the y-axis, you have your error rate, and on the x-axis, you have either throughput or power or hardware cost or whatever it is. And ideally, you want to stay in the lower left-hand corner, right? You want to have 0 errors and 0 cost, right? This is what you're aiming for. And of course, that's not possible. So what you're looking for are the Pareto optimal points within these graphs, right? So this is what it's all about. So we're looking for the sweet spots, the best combinations within this multidimensional design space that give us these Pareto optimal implementations. And there's basically 2 ways on going about it. One is we can change the algorithms, we can change the data set that we're training, we can change topologies, right? So we can transform the algorithm, or conversely, we can work underneath the hood and try to customize the hardware architectures. And since we're an FPGA company, we're doing an awful lot of customizing. Okay, so in essence, we're doing a bit of both. And let me tell you in more detail about it. But the key concept that we're doing is that we're actually leveraging reduced precision neural networks to build end systems for embedded compute environments. So, and now we're diving straight into the research. Okay, so why is reducing precision such an interesting idea? There's a number of reasons to it. The first of all is that the cost of implementing, for example, a 1-bit operation over the cost of implementing a 32-bit floating point operation is massive. There's a massive difference. In fact, if this would be like the area, the grid that we have of 100 squares, the red one is the size that it would take to implement a 1-bit operation, and the whole grid would be the cost of implementing a 32-bit operation. So you're basically shrinking the size of the operator by a factor of 100. And what that means, I can instantiate 100 more of those in the FPGA. And because neural networks are incredibly parallel, right, I can really take advantage of that, and it basically translates into 100x compute performance, right? So I get 100x more gigaops by shrinking the precision of the operator. So that means today's devices can scale up 200 teraops, right? It's a huge number of performance. So that makes it really attractive. The second aspect is, if I look at my neural network size, right? Remember we were talking hundreds of megabytes for popular neural networks. So if I have to store, instead of 32-bit, 1-bit data types, I shrink the memory cost exactly by 32, right? It's easy. It's a linear scaling with the precision that I have. So when I scale by 32 hundreds of megabytes, I actually get into a range where I can stay completely on chip, right? Which means no external memory components. I can make the implementation smaller. I can save power. Life becomes awfully easy. So those are 2 very powerful arguments. The third argument to this is that reducing precision and going from floating point to fixed point representations inherently saves power. So, for example, if I take a 32-bit floating point addition, right, and I go to a 32-bit fixed point addition, the energy that it requires per operation goes from 0.9 to 0.1 picojoule. So I save 9x just by going from floating point to fixed point. And then on top of that, when I go from 32-bit to 16-bit to 8-bit, and so on, I can serve another order of magnitude in terms of power consumption. So, and that's the third reason of why reduced precision makes sense. So the big question is, do we actually lose accuracy when we do this, right? Because we're taking information out of the neural network and throw it away. So what happens here? So here's some experiments that we've done. So we've taken a convolutional neural network and we implemented it with floating point. And then we doubled its size, and then we doubled it again, and so on. And we plotted here on the y-axis again error rate, and on the x-axis is the amount of compute resources that it requires. And notice this is a logarithmic scale. So the green line is the floating point implementation, and then as it comes down, we always double the size of the neural network. And you can see error rate goes down, right? Which is what you would expect as you throw more neurons at the problem, but hardware cost significantly increases, right? And it's a steep increase. Then we've taken the same networks and we quantized it 16-bit, which is the blue line. Then we quantized it to 8-bit, to 4-bit, to 2-bit, and to binary. And what you can see is, well, as you quantize them further and further, hardware cost reduces and error rate goes up. Now the interesting bit is, let's say I have a target error rate of 11% and I have an 8-bit implementation of a neural network. When I take that and take it down to 2-bit, I lose accuracy, right, as you would expect. But the nice bit is I can actually double the size of the network again, right, and I come out at the lower orange square. And that one has actually a better accuracy than the 8-bit implementation. And on top of that, it requires less hardware resources. So those are exactly the design compromises that we're looking for. So you don't necessarily need to lose accuracy. There are ways for compensating it again. The second aspect to this in regards to accuracy, there is new training methods being thrown at quantized neural networks all the time. And this graph shows you over the time the best reported accuracy numbers, top 5 error rate for ImageNet classification. And you can see the red line is the floating point, right? You have the ImageNet competition winner, and you can see they're down by around 3% now, whereby the improvements are only marginal now from year to year. On the upper dots there, the blue line are binary neural networks, which were introduced at the end of 2015, and you can already see they're massively increasing in accuracy. And the quantized versions, like the green dots and the gray dots with, let's say, 2-bit representation, 3 bits, 4 bits, whatnot, they're coming now very close to the originally floating point implementations. So I'm absolutely convinced that over the time, this accuracy gap will actually be closed. So let's take a look of what we're doing now with the customized hardware architecture. So we already talked about what happens, right, when you take the operands and the arithmetic units down to a reduced precision, how they get smaller and smaller, and I think that's not hard to understand. But the second aspect is that we're actually building customized data flow implementations for neural networks. So let me try to explain how that is actually different from a GPU implementation. So if you take a neural network on the left-hand side and you run it on a GPU, what you do is you take the first layer, you throw it on the GPU, you compute it. Then you take the second layer, you compute it, the third layer, and so on. So it's one layer after another is the way it's kind of run. So it schedules the neural network on top of a fixed compute architecture. What we do on the FPGA is we basically build the neural network in hardware. So we completely unroll it in the FPGA. Now we need to fold it back a little bit because obviously the neural networks are massively complex. but what we have a one-to-one representation of the neural network topology within the semiconductor device. And what happens then is you have a pipeline architecture that will execute the images as they flow through, right? And that brings you inherent advantages, such as, for example, latency, because you don't have to iterate over images. Oh. Okay, so those are the key ingredients that allowed us to produce some of the results. So there's a lot of graphs that I have. To make it simple, I mean, you have again, these are all these charts with error rate on the y-axis. On the x-axis, we have throughput. So for now, on this one, you want to be to the far right and low down. And you can see the orange dots are the single precision floating point. Then you have the blue dots, which are the 8-bit neural networks. The gray dots are the extreme ones with 1-bit weights and 2-bit activations. And you can see, as you reduce the precision, you get a massive throughput improvement for that specific ImageNet classification task. So these are we're providing faster solutions by reducing the precision. The second bit is the solutions get cheaper. So now we have the hardware cost on the x-axis, so we want to be back down in the lower left-hand corner. And there you can see that the gray dots bring you basically to the left-hand side. The accuracy isn't so great on those ones yet. The 2-bit weights and 8-bit activations are looking pretty attractive. So it's always a compromise. So if you have, let's say, a specific cost envelope that you have to fit your solutions into it, then maybe you have to trade off a little bit of accuracy. Whereas if your error rate is the limit, then maybe you have to increase the precision again. So there is, depending on what you're looking for in your end solution, there is a different trade-off to be taken. And finally, you get to save power, right? So this is auto transition enabled. Okay, so this axis you have picojoules power consumption on the x-axis, error rate on the y, and you can see as you go from the orange, blue, yellow to the gray dots, you're actually reducing power again in exchange for a modest decrease in accuracy. Okay, so that's basically what we've done. We've built numerous demonstrators, for example, a robotics arm that can play solitaire on a tablet device that was actually on television the other day. We have YOLO demos built on embedded compute systems. I'm not sure whether you've learned about YOLO networks yet, which can recognize not just one cat in a picture, but multiple cats and dogs and at different locations. So it can do multiple objects within a picture plus identify where in the picture they are. So we've built those already on our devices. We had it exhibited at numerous conferences, patents and publications out, which is our bread and butter in industrial research. And perhaps of interest to you, we've built open source releases on our PYNQ embedded compute platform. Let me show you this on the upper right-hand corner. That's the platform. It's called PYNQ because, not because of the color, because the spelling would be off anyhow, because it's Python enabled and it's running on one of our devices, which is called Sync. So that platform is actually very cheap. It's only $65. Do I still have time? Yeah. Which has two ARM cores on it and an FPGA fabric inside it, boots Ubuntu. It has Python APIs to talk to the FPGA accelerators, and we built a number of example designs with neural networks which are packaged in Jupyter notebooks, so they're really easy to follow. You can download them off GitHub and maybe experiment with yourself. We're also putting together a robotics kit, which is loads of fun. There's lots of AI-enabled embedded compute systems that you can build with this. And much more to come in the future. So with that, I'm already coming to the end of the talk. So there are a number of things that I wanted to get across to you. First of all, deep learning is a real challenge for the semiconductor industry. There's numerous solutions, right? GPUs are building solutions. There's custom ASICs coming out because it's such a huge topic. Custom architectures on FPGAs and together with reduced precision neural networks can enable real-time processing on embedded compute systems at very low power consumption. We've demonstrated a number of customized algorithms on architectures with our research, proving significant value, especially with the reduced precision and the data flow architectures. We have top-in-class performance and compute efficiency with very low latency. But we're scratching the surface, right? There is so much more to understand, different quantization schemes, different numerical representations, you name it. There's a huge amount of research still open. And so I would encourage you to take a look at it. It's a very exciting subject. There's a lot you can achieve with it. And also, I would like to generalize and just emphasize that this is not a unique thing. This is one of those computer engineering challenges that we will increasingly see in the future as we in the semiconductor industry are struggling with performance scaling. So with that, that's all I had. I have no idea where the time is. There's no clock here. So thank you.
Thank you very much. That was absolutely excellent.
Thank you.
I have one question for you. How do you train a binary network? How do you?
How you train them? Okay, so there's a number of training frameworks that support in separate branches the reduced precision implementations. And the way it's done is you basically quantize during training the weights. So you carry the quantized as well as the full floating point representation of the weights during the training phase, but then you always quantize after the activation functions.
Okay, so you basically do the training in floating point, but
you quantize always directly after the activation function.
Right. Okay.
But yeah, but
so you do the evaluation. You evaluate the forward pass. You do it with a quantized
exactly
version. The back propagation is done with floating points.
That's right. That's right.
Any questions? Yes.
As you have mentioned in the lecture, is like if you have the same bits precision, the floating point operation basically takes more energy and consumes more power than a fixed point operation. Can you just, my question is why does it do? I mean, what is the reason for the floating point operation generally takes more power?
Takes more than a fixed point.
Yeah.
Yeah, okay, that's the point. So for example, if I do a floating point add, and you know floating point, you have your mantissa and your exponent, which means the decimal point in the two numbers that you have can be at different positions. So if I add them, the first thing I have to do is I have to normalize, which means I have to blow up the value, right? And then I can add, and then I can basically, whereas with fixed point, the decimal is directly at the same point. That's why floating point is very expensive, not only in power, but also in terms of hardware resources.
The second question is, as you have said, GPU, in GPU you can have basically better precision computing rather than it basically serves with a lot of latency than the FPGA. So do you think that if you have a kind of multi-processor system in chip, MPSoC kind of devices where GPUs work hand in hand with FPGA, where some of the stage you feed it to GPU where you need more precision for that particular stage, and the later stages or the intermediate stages are actually performed by the Xilinx processors, FPGAs, where you get it with less latency. So do it basically over in all.
Yeah, you're asking a big question. You're asking a big question. So first of all, this idea of combining different types of compute fabrics into the same device is exactly where it's going. We're calling it the, God, it's a mouthful, the era and in diversification of increasingly heterogeneous compute platforms. Okay, so which means the devices are getting more and more complex. Because we don't have a free lunch anymore, right? We have to specialize certain parts of the circuit to different types of tasks. And because of that, we will have to build many more of different types of devices for different types of markets. So that's a fact, and that's definitely happening in different forms. So for example, there's FPGAs coming out with hardened floating point support, right? Which, for example, would help with the higher precision if it's really needed. I yet need to be convinced of that. That's a fact. There was a second part to your question. Remind me.
Yeah, the multiprocessor system in chip-like system where basically...
Oh, the data flow versus the, yeah. So I think, God knows what NVIDIA is going to do next, but guaranteed they will start implementing elements of data flow in their GPUs. And in fact, they're also going down in precision, right? So they have half precision tensor cores now, and some of the devices in the Pascal family even have fixed point 8-bit integer, right? So they're doing the same thing, and there's a good reason for it, right? Because you inherently can pack more compute inside the device by taking more efficient numerical representations, and secondly, you save power.
Excellent. Time for one last question, maybe.
When you say that you need to customize the architectures or the FPGA, what are your parameters that you change from one application to the other?
So
is it a physical silicon that gets customized?
No. It's literally the architecture that I instantiate inside the FPGA. So if I just go back quickly. Yeah, so for every neural network, for example, I generate a different architecture because it's so, for example, if the first layer has 10x the compute of the second, I will give it 10x more resources. So there's a direct mapping between the compute requirements in the different layers and what's created inside the FPGA. And the second part is, of course, I customize the operators to the precision. Right? So I can.
The chip is the same. You're using the same chip.
Yeah, exactly. It's in the same device. But so, for example, in the first layer, I can, let's say I get RGB images in, right? So I have 3 channels with 8-bit. So I'll operate on 8-bit representations. Whereas in the second layer, I might already go down to 1-bit or 2-bit. So it's all about really customizing the neural networks to find that sweet spot and my design space trade-off.
All right, thank you very much, Michaela.
Okay, thank you. My pleasure.